classes on fundamentals of electrical engineering. We are still on electrical machines, but we have moved on to transformers. And in transformers, we are going to have two sections. And in each section, we have three sessions. So this is the second session in the first section on transformers. Okay. Earlier we discussed basics of transformers, which included some construction aspects, some voltage relations, and also base impedance and things like that. But now we'll move on to mostly efficiency. Okay, efficiency and to some extent regulation. Okay. So let's look at, some of the questions are similar, so they've been clubbed together to the extent possible. Okay. So for the first problem in this area, now we go directly into problems, happens to be that the efficiency of a 100 kVA transformer is 0.98 at full as well as at half load. For this, the transformer at full load, the copper loss. Okay. So we want to have the copper loss. Okay, so how do you do that? Okay, so we are given that the efficiency is the same. Okay, for both cases. So we equate 0.98, okay, that is the efficiency, as equal to, let's say, 100. Okay, so in all these cases you can take 100 kilowatt or megawatt, whatever, as the output. Okay, so 98 divided by 98. Okay, so that is output divided by output plus losses. So what are the two other losses? One is WCU, the other is WI. Okay, so that is full load. Okay, but when you talk about half load, 98 becomes 49. So both on the numerator as on the denominator, and copper loss becomes half square of 0.25 WCU plus WI. Okay. So now, so in 0.98 has now been equated to both the situations. So now it's just arithmetic manipulation. So what is preferable? Multiply numerator and denominator by 2 for the second equation. So for the second, there is the right hand side. Okay, so that becomes 98 divided by 98 plus 0.5 WCU plus 2 WI. Okay, so now the numerators are the same, so the denominators can be equated. Okay, so we see that the denominators of the first expression and the third expression. Okay, so please remember the second expression has been manipulated to see that you can equate the both. Okay, so we see that 98 equal to 98. Okay, remove that. WCU is equal to WCU plus WI is equal to 0.5 WCU plus 2 WI. Okay, so simply you can calculate 0.WCU is equal to WI, because that's the addition there. As simple as that. So we can see that that is half the copper loss is iron loss. So which is bigger? Copper loss is bigger. That's all. That is more than copper loss. That's all that's asked. The problem is done here, but without doing the problem itself, you can remember that. You can realize that copper loss has to be larger, because the iron loss does not make much of a dent in the efficiency calculation, though the load has come down by half. Okay. So now we are having the second problem. A single phase transformer has no load loss of 64 watt. Okay, as obtained from an open circuit test. When a short circuit test is performed on it with 90% of the rated current flowing in its both low voltage and high voltage winding. So now there's only 90%. Okay, the loss measured is 81 watt. Okay, so now with 91%, the loss is 81 watt, and that's the copper loss. Okay, so it's very clear that that there is the full load loss would be different. How much would it be? K square. Okay, K square W is equal to 81. Okay, and that K square, K is already given, is equal to 90%. So it's very clear that the total loss is equal to 100 watt. Okay, yeah, the transformer is maximum efficiency when operated. So that's what we are trying to find out. The full load copper loss, as was mentioned earlier, 81 divided by K square, that is 0.9 square, gives us 100 watt. Okay, and now we want to have K2 into 100 as equal to 64, because maximum efficiency is obtained when the no load loss of 60, when the short circuit test is performed on it with 90. Okay, now the transformer has maximum efficiency when operated. Okay, so maximum efficiency is when the copper loss is the same as equal to iron loss. Okay, so we need to have the no load loss as equal to 64 watt as equal to K square into 100. So K can be calculated as equal to 64 by 100, square root of that, so it's equal to 80%. Okay, so these are some of the recurring aspects. Okay, one is of course at maximum efficiency, the iron loss should be the same as equal to copper loss. Okay, so at that time copper loss will be dependent on a particular load. Okay, so a load factor needs to be considered. Okay, so and that will be appearing as copper loss as K square times the full load copper loss. Okay, so those things can be remembered. That's all. Okay, It's actually very simple because the kinds of questions are repeated. A little bit of computation is required. Third problem is a 500 kVA three-phase transformer has iron loss of 300 watt. Okay, so which includes both. Okay, that is hysteresis and eddy current loss. Okay, and full load copper loss. So here hysteresis is not talked about. Full load copper loss of 600 watt. So WI is equal to 300, WC is equal to 600. The percentage load at which the transformer is expected to have maximum efficiency. Very clear because very easy because k square times the copper loss should be equal to 300. Okay, so you can calculate k as equal to 0.707, or this is the load factor. Okay, so at this time the efficiency is maximum because iron loss is the same as equal to copper loss. Okay, similar questions arrive exam after exam. So the fourth problem, a single phase transform has a maximum efficiency. What do you mean by maximum efficiency? Copper loss and iron loss are equal. So k square into WC is equal to WI. Okay, and efficiency at 90% at full load and unity power factor. Okay, that's good. Efficiency at half load at the same power factor is what? Okay, so power factor is unity power factor. Okay, so now efficiency at half load is required. So now maximum efficiency is 90, where 5 so we just assume that the output is 90, so the input is equal to 90 plus the two losses. Okay, so the two losses are now equated because it's maximum efficiency. Okay, so 100 minus 90 is 10 is divided into 2, so 90 divided by 90 plus 90 plus 5 plus 5, where 5 is copper loss, full load copper loss, and 5 is iron loss. Okay, so that gives you 90%. Okay, so this is just assuming that 100 kilowatt or 100 megawatt or whatever, or 100 watt happens to be the input, of which output is only 90%. Okay, and now at half load the efficiency will be given by 45 because from 90 we have come down to 45 divided by 45 plus 5. The iron loss remains the same, but because it's half load, 1/4 the copper loss alone exists. So 45 plus 0.25 into 5 plus 5. So that obviously give us an answer of 87.8%. Okay, so the answers need to be calculated, that's all, but of course the method continues to remain the same. Okay, fifth one, a 300 kVA transformer has 95 efficiency at full load at 0.8 power factor lagging. Okay, and 96 efficiency at half load unity power factor. So there are two cases. One is 95% at full load. Okay, so WCU is equal to WCU and 0.8 power factor lagging. Okay, so that's also there, and 96% efficiency at half load unity. Okay, so the problem is done. There's a second portion for it, but still let's see. We can see that yeah, so and what is required is the iron losses in kilowatt under full load operations. Okay, so what are the, and another question which is related and which has been done together is that 300 kVA transformer, as was mentioned earlier, has 95% efficiency at full load, 0.8 power factor lagging, and 96% efficiency at half load unity. Okay, unity power factor. Okay, yeah, so unity power factor. Okay, so what is the maximum efficiency at unity power factor? Okay, so let's see. We will divide. So first and foremost, we must remember that we are having we are having an output. Okay, sorry, an input as given by, in the first case, 240 divided by okay, so 300 kVA is the output. Okay, so the 300, okay, so what is given is always the output. Okay, so now multiplied by 0.8 by, because it to convert it into kilowatt. Okay, so 300 kVA multiplied by 0.8 is 240. Okay, so 240 divided by 0.95, what does it give you? It gives you the input. Okay, so input minus output. What is output? Output is 240. How do you get 240? 300 into 0.8. Okay, so 240 divided by 0.95 minus 240. Okay, what is it? That's the losses, because input minus output is going to be the losses. So input again is 240 because divided by 0.95, and output is 240, and both the 240s are obtained out of 300 multiplied by 0.8. Okay, so that gives us 12.63, and that's the same as equal to WCU plus WI because it's full load. Okay, now let's move to the next question, next part. What does it talk about? Half load. Okay, 96% efficiency. So half load and unity power factor. What does it mean? 300 into 0.5 into 1 unity power factor. So 150 divided by 0.96. Why? The efficiency is 0.96. So what does it give you? It gives you the input. So input minus output. What is output? 150. So 150 divided by 0.96 minus 150 will give you the half load copper loss and the ordinary, the constant iron loss. So WI plus 0.5 half load. So 0.5 square is 0.62. Yeah, so that gives you 0.5 square is 0.25 WCU. plus WI. So 12.63 is equal to WCU plus WI, and 6.25 is equal to 0.25 WCU plus WI. You solve it, you see that WCU is equal to 8.51 and WI is equal to 4.12, and that forms the answer as the C option. Okay, so that part is over. Now we need to find out the efficiency. Okay, so the next question is maximum efficiency. So how do you find out the maximum efficiency? When copper loss, the load factor square multiplied by copper loss is equal to iron loss. So K square into 8.51 should be equal to 4.12. That when you solve, you see that K is equal to 0.696. Now it's simple. 300 into, again it's unity power factor, so 300 into 1 into 0.696 divided by 300 into 1 into 0.696 plus we have 2 times the iron loss, because the copper loss should be the same as equal to iron loss, and iron loss remains constant, so 2 into 4.12. That gives you the maximum efficiency as 96.2. Okay, so in all these aspects, just some manipulation and the basic understanding of 3 or 4 features. One is of course that in this case we extended a little further. We said that output, okay, of course the power factor needs to be taken into consideration, the load needs to be taken into consideration. Once both these aspects are given, you get output. Okay, so because output is specified in kVA times, in that case a kilowatt has to be obtained, and then based on the power factor there is an output. Okay, so output divided by efficiency will give you the input. Subtract the output, you get the losses. There are 2 losses. One is the iron loss, which remains constant, the copper loss, which is load factor dependent, and it's equal to K square times WC. Okay, so based on these things you can find out the efficiency at any power factor, at any load, and also the maximum efficiency, at which time the iron loss is the same as equal to copper loss, or in other words, copper loss is the same as the iron loss, or K square times the full load copper loss is equal to iron loss. Okay, which remains constant. Okay, so next problem is the percentage resistance and reactance of a 10 kVA 400 volt by 200 volt 3-phase transformers are 2% and 10% respectively. Okay, so this is a little different. The percentage resistance and reactance are given. Okay, if the constant losses in the machine are 1%, maximum possible percentage efficiency of the transformer is asked. Okay, so we are given that there is a full load copper loss as given by, because this is 10 kVA, we'll take it as there's no so we can see that there is a resistive content, and so we'll take it as 10 kilowatt multiplied by 0.02, because the resistance is 2%. Okay, so that gives us 200 watt. Okay, so iron loss is the same as equal to 10 kilowatt, again multiplied by 0.1, because we 0.01, because that gives you the inductive content. Okay, so that's equal to 100 watt. Okay, so load factor for maximum efficiency will be given by K square times copper loss, or K square into 200 being the same as equal to 100. So we see that load factor is equal to 0.707. So efficiency maximum can be easily calculated as 10. That is the output kVA. So 10 which has been converted into kilowatt, because unity power factor is considered all through. So 10 into 0.707 divided by 10 into 0.707, or 7.07, plus 2 times the iron loss, okay, which is equal to 100. Okay, so that gives you 97.25. Okay, so the same concepts repeated again and again. Okay, so in the 8th problem, in transformers, which of the following statements is valid? Let's be very careful when we read. In an open circuit test, copper losses are obtained, while in short, no. Okay, we can discard immediately. Always the open circuit will give you the no load, that you give the voltage. Okay, so normally it is related to the flux, so you will always get the iron loss. Okay, in an open circuit test, current is drawn at high power factor. No, it is always the inductance which is governing the no load test, so you will have a low power factor. Okay, in a short circuit test, current is drawn at 0 power factor. That's also not true. Then the power factor is actually better. Okay, in an open circuit test, current is drawn at low power factor. Of course, that's exactly that's the only one which is okay, relatively true. Okay, so moving on to the next 9th problem. That is, it is desired to measure parameters of 230 volt, 115 volt, 2 kVA single phase transformers. The following wattmeters are available in a laboratory. Okay, so W1 250 volt, 10 ampere, low power factor. Low. So normally you do open circuit test by keeping the secondary open and giving the entire voltage, the full voltage, because flux is related to the voltage. Okay, and then at that time the power factor is low, so you use a LPF wattmeter. Okay, so that's the general trend. And then when you do the when you do the when you try to find out the copper loss, you normally go for switching the primary and the secondary are interchanged, and you give lower voltage, but but with a better power factor wattmeter. Okay, so that's it. That's it. So let's see what are different wattmeters. There are two low power factor wattmeters. So 250 volt of 10 amps and 5 amps. So 5 amps will do, okay, because we are doing what is called as a no load test. Okay, so or we are doing an open circuit test. Okay, so there is an answer where in W2, yeah, there are two answers with W2. So we might use one of them, but yeah, so we don't require 10 amps. Okay, so W1 is not required. Okay, and then we move on to, yeah, W3 is 150 volt. Okay, 10 amps is good, high power factor. Okay, so copper loss, that may be good. Okay, so W2 and W3 happens to be the best combination. Of course, in this context, W4 with 150 volt and 5 ampere, though it's high power factor, won't be enough because the current seems to be 2 kVA divided by 230 or 2 kVA divided by 115 will give you a bigger current. Okay, so that's it. Option D. Okay, 10th, 3 phase 900 kVA 3 kV by root 3 kV delta star. Okay, so on the primary the phase voltage is 3 kV, and on the secondary it's going to be root 3 by root 3 or 1 kV as the secondary. Okay, has primary high voltage side and resistance per phase of 0.3 ohms, and secondary low voltage side resistance per phase of 0.02 ohms. Iron loss of the transformer is 10 kilowatt. Okay, everything is fine. Yeah, so then we are having yeah, and this is 10 kilowatt. The full load efficiency, percentage efficiency of the transformer operated unity power factor is what? Okay, so now we are having full load output at unity power factor is 900 kilowatt. Okay, because 900 kVA can be now multiplied by 1 for unity power factor, and it can be full load also. So it's again another multiplication by 1, so 900 kilowatt. And K is given by 3 divided by root 3 by root 3. Okay, because as 3 by 1, because we already talked about the secondary phase voltage being equal to 1. So K is equal to 3. Okay, total primary resistance is not just 0.3, whatever is reflected and given there. Okay, so we are having total primary resistance as given by 0.3 plus 0.02 on the secondary multiplied by K square, that is 9. So it is equal to 0.48 ohms. I suppose this is clear. Okay, and then we also have full load current as equal to 900 divided by 900 kVA divided by divided by 3. That is we are trying to find out the full load current. So 900 that is divided by 3 is for per phase, and then again because it's a delta divided by 3. Okay, because that's 3 kV happens to be at the primary the primary applied voltage. Okay, so it gives us 100 amps. I suppose it's clear. 900 by 3 is okay because it is per phase requirement, and then divided by another 3 kV because it is kV, you can divide by 3 directly, so you get 100 amps as the full load current. Okay, so full load copper loss is the same as equal to 3 times because we are having in each phase. Okay, so we have already taken care of only per phase resistance, per phase current. So 3 into 100 square current multiplied by 0.48, which was calculated right now after reflecting the resistive components on the primary onto the secondary. Okay, so totally we are having 14.4 kilowatt as the full load copper loss. Okay, and then 10 kilowatt is given as the iron loss. So efficiency is easily calculated as 900 kilowatt. Now it is kilowatt, unity power factor and full load. Okay. So 900 divided by 900 plus 10 iron loss, and then 14.4 which we calculated as copper loss as equal to 97.36. Okay, so how did you calculate copper loss? By first and foremost finding out the total resistance. Okay, so the primary resistance is not just 0.3, but of course it's also 0.02 reflected onto the primary using the k square quantity, which is the square of the turns ratio. Okay, so we are having 0.48. Okay, and then again, how do you find out the primary full load current? Okay, on the primary side, you divide 900 by 3 such that per phase quantity is obtained, and then divide by 3 kV because 900 happens to be kVA. Okay, so you get 100 amps as the current. Okay, then 100 square into 0.48 will give you per phase copper loss multiplied by 3. So 14.4 happens to be the full load copper loss. Okay, so as simple as that, and in all 3 phases. Okay, so you can work with on the 3 phases together. Okay, so 11th problem is 10 kVA 400 by 200 volt single phase transformer with a percentage resistance of 3%. Okay, if you are given 3%. Okay, so once you follow this portion again and again, it will be very clear that you will be able to do any problems. Okay, these are a little tougher problems because certain things are overlooked. Okay, but please don't overlook. Okay, and percentage reactance of 6% is supplying a current of 50 amps to a resistor load. The value of the load voltage is what? Okay, so so there is a load and then you are giving your voltage. Okay, how do you do that? Okay, so of course, since we are working with percentage etc., you can always find out the base impedance. Okay, what's the base impedance on the load side? That's on the 200 volt side. Okay, so that's given by. So you can choose your side. Okay, so you are choosing the, because the load is on that side and you want the voltage there, so you want a reduction of the voltage on the secondary impedance. Okay, so that's the reason why you're trying to find out the impedance on the base impedance on the load side. So what is it? 200 square kV square or voltage square divided by kVA multiplied by 1000. Why? Because you are choosing 200 into 200, which is volts. Okay, so 200 into 200 divided by 10 into 1000, because 10 happens to be the kVA. Okay, so that's equal on both sides. Okay, so that's equal to 4 ohms. Okay, and now this 4 ohms now when multiplied by the per unit value, now given in terms of in percentages, that is 3%. So 0.03 multiplied by 4 gives you 0.12 as the ohmic quantity. And similarly, in this resistance, there's a drop as given by 6 volts. So remove it from 200 volt, you get what is called as 194 volt. Okay, as simple as that. Okay, so now let's move on to, because it's a resistive drop. Okay, that's why we are taking only the resistance. Okay, so that's all for today. I hope the problems are clear. Here we have chosen only resistive drop because the load happens to be resistive in nature. Okay, so but the other drop will be at 90 degrees. So this is enough. So, and the other answers are a little too away, or 192 and 196 are not correct. Okay, so now we move. So we also saw that we have to be careful with respect to the base impedance. Okay, how do you take it? On which side do you take it? Okay, and whether you estimate it using kVA, voltage, etc., VA or MVA, etc. Okay, so be careful. And so the side on which you take the impedance, and once you have the impedance, you can try to separate out the copper loss if you are separating out the resistance, or you can use drops, etc. Okay, so there are, okay, so the watt meters that you choose happen to be at low power factor to get the open circuit or the iron loss, but copper loss is occurring at a high power factor because it's essentially resistance of the circuit. Okay, so we also see that we also see that the percentage efficiency can be maximum only when iron loss is equal to the copper loss. Okay, full load copper loss has to be multiplied by k square. The k refers to the load factor. Okay, so so if there's a load factor, it will get it will be used for the out to estimate the output as also the copper loss. The iron loss remains constant all through. Okay, so and moreover input minus output is equal to two losses. Okay, copper loss and iron loss. Okay, if a full load is given, then the WCU is going to be the full load copper loss. On the other hand, if the load factor is there, then you have to multiply copper loss by the square of the load factor. Okay, so so I suppose all aspects were talked about, and you will be able to do these kinds of problems. As I said earlier, they are repeated, and you'll be, once you've got the hang of it, it will be easy to do them. Okay, so thank you.